Hello, people. Welcome back. So, the other time we went over the first part of the atomic structure, the timeline that it followed from Leucippus all the way to J.J. Thomson. So, but there are some few things that I want to touch base on with J.J. Thomson before I move on to other contributing factors of the atomic structure, such as the Millikan's oil drop experiment, and then we go to Rutherford's alpha scattering experiment. Then we go to Chadwick's helium shooting experiment too. There are some few things that I want to take charge of. So, J.J. Thomson, as we know him, let me get a black pen. Joseph John Thomson. So when Joseph John Thomson did the cathode ray experiment to discover electrons, the term electron wasn't new. So there had already been experiment done by a scientist called Stokes, and he did he predicted the theoretical value of an electron, and what electron meant at that time was, the literal definition was the smallest charge, right, a particle can carry. That was electron. So when J.J. Thomson did his experiment, the cathode ray experiment, right, it goes like that, and then he has, and then he connected this to a battery. So when he did connect it to a battery, then he shot he shot the electron rays through. The rays go and then hit the other end of the fluorescent tube, and then he asked himself, what at all is this ray? So he decided to do some manipulation on it. He first connected electric field to this cathode ray tube. And here is our positive part of the electric field. Here is our negative part of the electric field. When he did this, something amazing happened. The ray of light, or the beam of light that was coming from the cathode rays, it bent, right? Now, it bent all the way to the normal, and it did not bend to any random direction. Direction was predictable. It bent to the positive side of the electric field, which means it was repelled by the negative side of the electric field. And then at that time, they knew that if a particle is attracted or propagates towards another charge, they might be opposite charges, because they were playing with electricity at that time. As I told you earlier, scientists like Faraday had already done electrolysis, so they knew how electricity worked, but not necessarily what electron was, right? So, and then he switched the electric field to magnetic field, right? Switching the electric field to magnetic field. Let's say here is a magnetic pole, your north side, and then the south side of a magnetic pole. Now, what happened to the beam after he switched it was that the ray did not stay straight. It bended towards another end of the magnetic pole, which means whatever this ray is, it is attracted by a magnet, and it is also affected by an electric field. That is where he came up with the idea that if it's repelled by electric field and then attracted by a magnetic field, it might be an electron, right? Now, the reason why they call it an electron was that J.J. Thomson, right, did not just end the experiment here. He used what we call the mass spectrometer, which is going to get into it later on, to calculate the mass per charge ratio of the ray that was being shot from the cathode ray. And when he calculated the charge per mass ratio, he found a figure, and then later on, that value put in by the Millikan's oil drop experiment, which also found the smallest charge a particle could carry. And then they substitute that equation into the charge per mass ratio. They found the charge of an electron. Do you understand what I'm trying to say? So that is basically how it went on, and that was the thing that I wanted to get onto before I moved on. When after he was done with it, he came up with a plum pudding model of an atom, which is basically a bowl of pudding. And as I said earlier, pudding is an English food with a beans stuck in it, right? So when he came up with this idea, the plum pudding, right? If you are an American, I told you think about this as a muffin, right? A blueberry muffin. You see have the whole muffin and what is stuck in it, the blueberries that is stuck in it. That was how he proposed the structure of an atom to be. That is basically like a muffin with electrons embedded in it. Now we know this is not true because earlier experiments refute this, and we're going to get into those experiments later on in the game. But right now, what we are going to look for, things that contributed to the alpha to the structure of an electrons were one. The next one that we're going to do was Mr. Robert Millikan. So this after J.J. Thomson in 1897, something like that, or 93, discovered the electron, right? Robert Millikan also set on an expedition to figure out the mass, to figure out the charge that the tiniest particle can carry, which in this case we can refer to the tiniest particle as an electron, but it was later down the line that they made that connection. So how was he going to do this, right? How is he going to find the charge, the tiniest charge that a particle can carry? He came up with an ingenious experiment, very much of a genius. He found himself a can, right? He found himself a can. So let's draw a can over here, right? Then let's go all the way down here. I don't have the straightest hands, so we're just going to go with what I draw, right? Right. So he had a can like this, right? And then on top of the can, like over here, he fixed an atomizer. Atomizer is basically the head of a spray. Like when you have like a spray, a deodorant, or a perfume, the top of it is called the atomizer because it pulls up the liquid, right? And then it splits it into tiny particles. That is literally like air, right? So that is basically what an atomizer is. And over here, he had an oil, right, tied to it. So we're going to say this is our oil. That he had. And let's say this is the bulb of the atomizer, right? So this is the atomizer. And then this is oil, right? So this oil, he knew the density of the oil, the volume of the oil he was using. Like he knew the physical properties of what he was using, right? And then what he did was that he put an electric condenser. So this thing right here is an electric plate that acts as a condenser. It's an electric plate that acts as a condenser, right? And over here, he fixed an X-ray right below the electric condenser. So let's say we have our X-ray projector here. So this is our X-ray. And this is our electric plate, right? So the electric plate, this was, say, the positive side of the plate. And let's say this is like, let's move here to be the negative side of the plate, and this is the positive side of the plate, like down here. And then over here, he fit like a microscope over here so that he could view through it, right? So this right here, he fixed a microscope. So now, what Millikan did was that he would spray, right? He would spray the atomizer, right, into this chamber. And then when he sprays it into this chamber, the particles place and then comes here. So when the particles place, which is basically atoms, right? Because it is an atomizer. So when the particles place, they fall into the electric plate, which also acts as a condenser. And when they fall into the electric plate, they get a little bit of charges, right? As they fall over here, they get a little bit of charge, right? But then as the charge that they were getting may or may not be enough, or maybe more than what is expected. So that was why we had he had the X-rays here, right? So what the X-rays did was that once the particles gets here, if the charges needs to be manipulated, the X-rays, X-rays carry charges. They basically use that charge to bombard whatever is here to give it charge or to take some charge away from it. And then they will fall all the way to the other end of the plate, right? So when Millikan was done with this experiment, right, he came out with some figures. As he was doing this experiment, something was becoming more and then more apparent, right? Once again, he sprayed an atomizer into this field over here, right? It goes into the electric plate, right? And then if the charge needs to be altered, it get hit by an X-ray and it will fall down. And the oil droplets, whatever is here, could be observed with a microscope that was mounted over here. So after the experiment, right, he came up with something amazing, right? He manipulated this plate because as he observed that the plate reacted to the charge and then vice versa, right? So what was happening over here was that there were some forces at play. If you have an object, or these in this case an atom, falling from like a higher level to a base level, we all know that gravity acts on it. So the one charge that was up in play was gravity, right? And then also as they become atoms, their masses become very light to the extent that electric field could manipulate them, right? So if electric field could manipulate them also, then one charge that works on it was also the electric field. So now we know the forces that is acting on the particles that are following through here. So let's come over here one more time. If they are falling, they are going down, we have a gravity, right? Which is the mass, the gravity, or is the weight pushing them down. So we have gravity acting down, right? But then the electric field could be manipulated to make the particles suspend, right? So if they are suspending or they falling back up, that is the electric field being manipulated. So if it goes up, it is what? The electric field, right? Now, we knowing that what Millikan did, right, was he observed so many particles, hundreds of them, right? Hundreds and hundreds of them, and then manipulated them. So he manipulated them to the point that the particles suspended in air, because one, he could see them. So that the particles could be suspended in air by viewing them through the microscope. And at the point where the particles were suspended in air, he figured that the amount of gravity, right? So the mg is equals to the charge or the electric field, which is, let's see, right? This is the equation that he developed. And when he developed this equation, he observed so many droplets, so many droplets of varying masses, right? What he found out was that any amount of charge that balances the mass that the droplets carry comes in a multiple of a number, right? Like a multiple of a base number. So the multiple of the base number that it came in was 160 zeptacoulombs, right? 160 zeptacoulombs. Now you ask yourself, why 160 zeptacoulombs? Why it wasn't not like maybe 80 or whatever? And then also, if you tell me that the charge that it could carry comes in multiples of 160, then I could also be like, well, isn't 160 a multiple of 2? Right? So why is the base charge not 2? Why is it 160 zeptacoulombs? Now, the reason why it is not 2 and it's 160 zeptacoulomb is because nature did not allow a particle to carry 2 mass and be balanced, to carry that level of mass and be balanced by a level of charge. He never observed a phenomenon like that, right, in his oil drop experiment, right? So in so doing, he came up with this figure, an experimental figure, right? And that became the charge that the tiniest particle, which in this case an electron, could carry. And then if you know zeptacoulombs is right 1.6 times 10 raised to the power negative 19 coulomb, right? So now we found the mass of the charge of electron to be this 1.6 times 10 power 19 coulombs. Zepta is 10 to the power 21. So if you jump 2 zeros, if you jump 2 decimal points, it's going to be 1.6 times 10 raised to the power negative 19, right? Let's put a pin in this. Now that they have this value, remember, J.J. Thomson, Joseph John Thomson, had already worked on the electron. And then what he found using a mass spectrometer, which is going to be our next topic of discussion, was the charge to mass ratio. So he found the charge to mass ratio of an electron. So charge to mass ratio of an electron. Now he found that to be the figure 1.7 times 10 power 11 coulombs per kilogram, right? So this is the value that he found, the mass to charge ratio of J.J. Thomson's cathode ray experiment. So now that we had this value there already, we did have this value there already, and we have come to find the charge here of an electron. What can we do? We could use these two values to determine the mass of an electron, right? So if the EM, right, is equals to 1.7 times 10 raised to the power 11 coulombs per kilogram, right? Then this is the charge, right? So we could substitute this over here. And if you substitute that over here, we're going to get 1.6 times 10 raised to the power 19 coulombs divided by the mass should give us 1.7 times 10 raised to the power 11 coulombs per kilogram, right? So now that we do have this, we go on and then make the calculations. Okay, so now that we knew that the mass to charge ratio of an electron is 1.7 times 10 to the power 11 coulombs per kilogram, and we know that the charge, the minimum amount of charge a particle can carry, which is an electron can carry, is 1.6 times 10 raised to the power negative 19 coulombs, or 160 zeta-coulombs. We could find the mass, and then we plugged in the values here. So if you do the simple calculation, we're going to find that the mass of an electron over here is going to be 1.6 times 10 to the power 19 coulombs divided by 1.7 times 10 power 11 coulombs per kilogram. So coulomb will cancel coulombs, and then per kilogram, you all know that it is times 1 over kilograms divided by 1 over kilogram. So it will flip, right? So then the mass will be, now if you're going to write the MCAT, which is our target here, and then the scope that we are going on this thing by, I think that you shouldn't do these calculations with a calculator, right? You should keep it in mind. So we're having 1.6 times 1.7, right? And it's something like 9.11 times 10 raised to the power negative 31 kilograms, right? Because this will flip and it will be a kilogram. So we found the mass of an electron from these two calculations. So in hindsight, what did the Millikan's oil drop experiment did for us? Of what importance was it? So one, it helped us to find the minimum amount of charge an electron can carry, right? And then two, help us to find the mass of the electron. So these two were the important things that the Millikan's oil drop experiment, Robert Millikan, in 1909, his experiment helped us find. And it was a really ingenious or a genius experiment for somebody to think about, atomizing oil, right? And then passing it through an electric plate for gravity to act on it, and having a way to determine or to figure out the amount of charge that it will carry. It has to be present for the atoms or the atomizer or the particles of the oil to suspend in air, right? So that he could coin an equation from it. And with the equation, use it to plot a graph as charge to mass, and found out that for any mass that the charge is going to carry, or the vice versa, it comes in a multiple of 160, which is 160 zeta-coulombs, 1.6 times 10 raised to the power negative 19 coulombs. So that is how they figured the minimum amount of charge a particle can carry, which is the charge of an electron that it can carry. That is Robert Millikan for you. He did a very amazing job in determining us to find the minimum amount of charge and then the mass of an electron. So the next person that we are going to move on to over here from Robert Millikan came some of the timeline that the structure is following is kind of accurate, or let me say accurate, because first Leucippus and then Democritus came and then did their philosophy work. Aristotle opposed, and then came John Dalton, made 5 postulates. They took 2 away. because John Dalton came and then refuted. And after John Dalton, we went to J.J. Thomson. So after Millikan, right, a scientist arose. Not that he arose, he was already there. Goes by the name Ernest Rutherford or Rutherford. Right. So Ernest Rutherford, before him, Millikan has already established, or the scientific community have already established, that the minimum charge and amount of the minimum amount of charge an electron can carry is 160 zeptacoulombs. Put 160 zeptacoulombs in your head, or you can put it 1.6 times 10 raised to the power negative 19 coulombs, or 160 zeptacoulombs in your head. And then they found the mass of an electron to be 9.11 times 10 power negative 31 kilograms, right? So now we do have these two fundamental quantities that we have come across, right? When Ernest Rutherford came into the equation, he did not came to challenge these or refute these. But what he came to observe was that he wanted to prove if Joseph John Thomson's experiment was real, right? He wanted to prove that is it actually true, right? That matter carries, is it true that the structure of an atom is like a plum pudding? So then he went to work, right? He and then his students, James Chadwick. So they went to work. What they did over here was they also tried to find a way to figure out if matter or an atom is made up of more than, just electrons stuck in a dough of positive charge structure, right? So he find a screen, right? Call it a screen. Let me draw like a screen over here, right? He found a screen, and then over here, he put a radioactive alpha particles, right? Alpha particles in some extent can be also called helium atoms, right? So he put a radioactive alpha particles here, and then inside the screen, he put a gold foil over here, right? A very thin gold foil. Like he made the gold foil so thin that it was just a couple of atoms thick, right? Like it was just few atoms thick. So they just shed away a lot of layers from the gold, and a very thin foil, they used it over here. Now, what he did was that alpha particles move really fast, right? They move there because as we could extend it to become like they are like helium atoms. They have mass, they have charge, they move super fast like zoom. So when they are coming on a scale of like an atomic scale, their momentum is enormous, right? So if what Rutherford was saying, that if J.J. Thomson's experiment was true and if it's hold valid, then anytime he shoots an alpha particles through the gold foil, which was a tiny atom stick, it should go straight through it. Like he wasn't expecting any repulsive forces, nothing. Because if you are telling me that it is just a dough, like a dough of positive charge embedded with electrons, then if I'm shooting, it's like I'm shooting what is it called? Like a ping pong ball, right? Through some type of like a very thin medium film of liquid, which has a little bit of debris in it. It should go straight through it. There shouldn't be any repulsive forces, right? So that was what Rutherford was hoping that he would achieve. So he came here, shot the alpha particles through it. So when he shoot through it, most landed here, right? And this was a fluorescence tube. So when the alpha particle hit the fluorescent tube, it light up a glow so that he knows where the particle ended up going, right? So he shoot through here, zoom. He will shoot it, zoom. He will get it here, zoom. He keep on shooting it. He will get it here on this side. But then occasionally, he will shoot it and it will end up over here. Like it will go through it, but then end up over here. Or he will shoot it and it will go up over here. Or sometimes he shoot it, it will end up over here. And shoot it, it will also come over here, right? In rare circumstance, he shoot it and it bounces right back to the shooter, right? So let's name this like alpha particle gun, right? That shoots alpha particle. And this right here, let's call it gold foil, a very thin gold foil. And then this is our screen, right? That lights up where the particle ended up, right? So after he discovered that, okay, so why in God grace scientific universe is when I shoot it, it end up over here, or when I shoot it, it comes over here, or goes over here, or over here, right? Keep on shooting it, and then it landed anywhere apart from this. And it wasn't that it landing here was like equal, like the amount of times it landed here was not equal to this. When you read into his experiment very well, it was every 1 out of 8,000 times that when he shoots this, it land anywhere apart from the expected zone that it was the particle was expected to land. So after Rutherford came with this experiment, what he found out, or what he ended up coining, or what he ended up coming up with, was that as Rutherford ended up coming up was, if the alpha particles was, if the positive charge was spread out inside of an atom, then the alpha particle should have gone straight through it. It should not receive any type of repulsive forces. But that was not the case. In every 1 out of 8,000 times that he shoot the alpha particles through the gold foil, it ended up somewhere on the screen that it was not expected. So then he said that since alpha particles gets deflected, right? Therefore, the positive charge is not spread out, right? He said that since it wasn't just going through it and then sometimes it will hit and then come back, then the particles was not spread out. Because let's take this for instance. If this is my atom, right? If this is my atom, and then you telling me that the whole of this atom is positive charge, but then I have like some electrons embedded into this charge, right? Then anytime I shoot an alpha particle through here, it should go straight out and come out the other end. Like anytime I shoot through, it should just land up. Like anytime I shoot through it, this is how it should be. There shouldn't be a deflection, right? But this is the case. And you might ask, wouldn't the electron have an effect on it? Let me scale it to you. For an electron, like comparing an electron to an alpha particle is basically like comparing a train to a human being. The alpha particles is huge on the atomic scale as compared to an electron. So electron would have no effect whatsoever in trying to repulse an alpha particle. So the electron doesn't even count at that point, right? Because they have known the mass of the electron from Millikan and J.J. Thomson. So they knew how much the electron would weigh and what effect it will have on the alpha particle. The alpha particles were essentially helium atoms once again. So let's move on from there. But any time that they shoot an alpha particle, zoom, and then it goes somewhere, or they shoot it, zoom, it ended up somewhere, or they shoot it, zoom, and it bounces back to them, right? Rutherford said something, right? He was like, okay, I don't necessarily think that the atom is a sea or a dough of positive charge, but rather the charge are concentrated in the center. The positive charge is concentrated in the center. So he came out with this model, right? That the positive charge is located in the center of the atom, right? And then around it, right, the electrons existed, right? So this is Rutherford's model that he came up with. So Rutherford came up with this model. If we examine this model, it made sense because, okay, if this was the model, then anytime we shot the alpha particle through it, if it does not come in contact with the nucleus or with the positive center of the atom, it should go straight through it, right? Then the alpha particle should all just go straight through it. But the moment you shoot the alpha particles, right, and then it hits the center, it could get deflected. Or you shoot it or in a hit, it could get deflected, or it could actually get bounced right back to you, right? Because then over there is a concentrated positive charge. So that was how Rutherford's model came to be of an atom. He discovered that the atom is not just a sea of positive charge, but then it is the positive charge is concentrated in a center, which most of the atoms is an empty space, and then the nucleus is right in the center with the electrons around it. So that was the Rutherford's model that it came to be. So after Ernest Rutherford and then J.J. Thomson had worked on the discovery of electron and improving on the atomic structure, a student of Ernest Rutherford goes by the name James Chadwick. James Chadwick. Now, James Chadwick was a student to Rutherford. But after Rutherford's experiment, he observed something. He observed that when you take atoms like hydrogen, right, and then helium, right, and if you are to measure the mass, if hydrogen is atomic number 1 and then helium is atomic number 2, right, then 2 of hydrogen, right, like 2 of hydrogen will give you 1 of helium. But then when he measures the mass, he found hydrogen, it takes 4 hydrogen to match up the mass of 1 helium. So the mass of a helium that he measured was 4 atomic mass unit. We will get into these units later down the line. And then the mass of the hydrogen that he measured was 1 atomic mass unit. So why does it take 4 of hydrogen to match up just 1 helium atom? It made no sense. So where is the excess mass coming from? Now, they made an assumption that the excess mass, right, might be coming from electrons, right? But then they have also done experiment and have proven that electrons are almost massless. Like their mass is so tiny, it wouldn't make any difference in the mass of an atom. So where truly is the extra mass coming from? So, and James Chadwick set on to do what we called, James Chadwick went on to do what we known as the beryllium-lithium experiment, right? What he did in order to achieve this was that he picked alpha particles, right? Like the one his boss used. And you might ask, where did they get the alpha particles from? At that time, they knew what radiation was. They knew what radioactivity was, right? So they were making they knew that they knew atoms that emit alpha particles when they are undergoing radiation, right? So they use those. And then he put a very soft metal here, like a beryllium metal, right? And then sometimes lithium metal, right? Over here. And he shoots the alpha particles towards it. So he will shoot the alpha particles towards the metal, right? And then when he shoots the alpha particles towards the metal, he get a release of some type of a radiation, right? He get a release. So radiation released, right? But then he did not know what these radiations were. Let's change the radiation into a different color. He didn't know what these radiations were, right? So he decided to manipulate it, just like the previous people have manipulated radiations and mysterious rays they did not know. They attach electric field to it. So he passed electric field to the radiation. He passed it through electric field, right? Positive and negative. There was no effect. Electric field had no effect on it. Then he switched up and then passed it through a magnetic field. That also did not have any effect on it. So the radiation has no electric field effect, right? Has no electric field effect. And then two, has no magnetic field effect. So the radiation cannot be manipulated by electric field, neither can it be manipulated by magnetic field. So how is he going to measure or see what these radiations are? And what these two tells us is that if it cannot be affected by both of these, it means the radiation carries no charge at all. And if a radiation carries no charge, how would you try to manipulate it, determine it? It limits your your observations and your thinking abilities on how to go about it. But what James Chadwick decided to do is to put a paraffin over here. Now, a paraffin is a substance that is rich in protons, right? Which is hydrogen atoms, right? It is very rich in protons. So he put paraffin here, and then he shoot the radiation to the beryllium atom or to the beryllium metal or the lithium metal, and then it will hit the paraffin, right? So when it hits the paraffin, right, the protons in the paraffin, which is the hydrogen atoms in the paraffin, gets kicked out, right, of the paraffins. So over here, we're like protons being kicked out, right? Over here is just protons kicked out. Right. So after the protons have been kicked out, he deduced his own, observations and then effects from it. He said, since these radiations were not affected by both electric zip, 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 and magnetic field, right? It has no charge. So the radiation has no charge, right? But since the radiation was able to kick out protons, right, which is heavy, they are almost as heavy as alpha particles over here, which the radiations were able to kick those out, it has mass. and the mass has to be bigger than electron because electrons can kick heavier particles out, right? So he also stated that the particles, right, has mass, and are heavier than electrons. So now that was established, it has no electric field effect, it has no magnetic field effect, means it has no charge. And then it's also being that it was able to kick out protons, means it has mass, and the mass has to be equivalent, if not the same or more than the mass of a proton, right? So once we was able to establish this, he went ahead and then say that, so in that case, because for the paraffin, the experiment kind of followed a similar effect as the Rutherford's alpha scattering experiment. Like when you put a screen here, it sometimes goes straight to it or it bounces back, it deflects, just as we said. So what was coined from over here was that atoms, as we know it, right, they have a heavy dense nucleus, right? So let's draw the nucleus. They have a heavy dense nucleus, but since Rutherford has already said that this nucleus is positive charge, is positive charge, right, which is protons, right? James Chadwick also said that the neutrons also exist in the nucleus of the atom because the reason why it is able to exist there is it has no electric field and magnetic field effect. It means it has no charge. And then having no charge means it cannot have any interactions whatsoever with the protons, right? So they can exist in the same space and cohabit. And then also it is heavier than electrons, meaning they could, if anything, the electrostatic or the what is it called? The gravitational forces of attraction between the electrons and then the protons will be equivalent, so they could hold each other in place because it has almost the same mass, and gravitational force is dependent on mass, right? So then over here, he said these parts are going to be your neutrons. So he said the atom has this heaviest, dense, thick nucleus, but the nucleus is made up of protons and neutrons, and then the electrons is on the side of the atom like that, right? So for him too, he did not know like the model that we do have today. Yes, still it was something like this, just that there is now a neutron and then a proton in it. So a quick recap of the atomic structure, right? The most relevant points, some points that could get tested, right? Because most of these are history. The points that could get tested was one, the discovery of electrons. So the discovery of electrons we know was done by J.J. Thomson, right? J.J. Thomson. Right. Okay, let me just erase this and then let's draw some type of a timeline diagram, right, for it. So timeline diagram, right? So first of all, we know that before any type of structure was coined, the original idea might have come from John Dalton, but Dalton did not propose any type of structure. He just made his 5 postulates, right? And then after John Dalton, there came J.J. Thomson, right? J.J. Thomson refuted Dalton's atomic theory by saying that matter has electrons, right, embedded in a dough. So from Dalton, and then what he did do 5 postulates, right? And out of the 5 postulates, 2 got eliminated, right? Eliminated. And why did the two got eliminated? Because of discovery of electrons and the discovery of isotopes. Okay, so from there we moved on from Dalton all the way to J.J. Thomson, Joseph John Thomson. J. Thomson, right? Now, J.J. Thomson did an experiment, and the experiment was called the cathode ray experiment. And what did the cathode ray experiment discover? The cathode ray experiment discovered electrons, right? After that, Ernest Rutherford. So from J.J. Thomson, we went down to Rutherford. So from that, Ernest Rutherford, right? Also did what we called alpha scattering experiment, right? And what did the alpha scattering experiment also did? What did the alpha scattering experiment did? It also made us discovery of protons, right? And then after Ernest Rutherford, his kid or his student came, which is also James Chadwick, right? James Chadwick. So James Chadwick also did his beryllium / lithium, right, experiment. And then what did that also came about? That came about the discovery of neutrons. So he based on his predecessor's determination of this scattering experiment to discover the neutrons. So far, the atomic structure went from, our atomic structure has moved from over here, as they already stated that atom was can neither be created nor destroyed, and then it is indivisible. Over here, it moved from this solid block by the first postulate, let's say by Dalton, right? Because Dalton said atom was indivisible, right? So let's say the solid block postulate was by Dalton, and then it came into J.J. Thomson. He came what we call the plum pudding, a pudding. If you are, pudding is an American, as I said again, a British dish. So it was just basically like a pudding with beans in it. That's why he said the atomic structure was. If you're American, compare you to a blueberry muffin, it's similar. So he said it's like this. Embedded in it is these electrons. So from there we went to Ernest Rutherford, right? What did Rutherford also say? Rutherford said that there is a positive nucleus over here. So this was made by, this was the alpha scattering, right? And then Rutherford also said this, the atom is a positive charge, a positive charge nucleus, right, with the electrons embedded around it. So from here we went over here, right, for Chadwick to say that now we have protons and then neutrons. biased to a sea of electrons, right? So this has been the continuation of the the atomic structure. So once again, more going over it, Dalton said it is a sphere, indivisible particle. J.J. Thomson said, no, there is electrons embedded in it. Then Rutherford said, no, there is a positive nucleus with electrons embedded in it. Then Chadwick came and be like, you're kind of right, but the nucleus has also a neutrons in it, and they are the same mass as a proton, but has no charge, and that's it. So these are the theoretical or the classical physics or classical chemistry side of the atomic structure. Now, from here, what happened was actually interesting, because from here, scientists start looking at an atom as a physical, measurable object. They started looking at it in a quantum level. We are going to browse over Bohr, Maxwell Planck's, Einstein's, what they also contributed in the structure of an atom, and we will do the hydrogen atom structure, and then from there we descend into proper calculation. So from now, this is the classical physics aspect of it. It is they treated it as a physical matter that can be manipulated, that can be measured, trained, and then have values for. But then the theoretical physics that we're about to get into, which would be we getting it more into the atomic structure, would be what we use today, the models that we use today. So for today, we will leave the video here, and then we will come next time, which is tomorrow, to discuss what actually contributed to the quantum atomic structures. And there is a very good instrument, a powerful instrument that helped them build this. It was called a mass spectrometer. So that is what we will tackle the next time we take on this topic again. So for now, all I can say is click on the next icon or the next button for the other part of this video.